My name is Sudeep George, and I'm the VP of Engineering at iMerit. Welcome to this session on training data for effective AI deployment. In this session, I'll be discussing about data-centric AI and edge case platforms and how they can help you as you go about deploying your AI systems into production. At iMerit, we provide data intelligence for production AI. We do this by working with a broad spectrum of companies and help them in structuring and classifying the data that they use for training their ML models. We also provide actionable data insights that are used for test case generation, edge case management, and anomaly detection. Our mantra is talent, technology, and technique. We have a large committed workforce that consistently deliver at high levels of quality SLAs that help distinguish us from our competition. We are an enterprise-grade company and offer HIPAA and SOC 2 compliance. Many of our workforce teams are also subject matter experts in various AI domains. We work with multiple customers in building complex AI systems by partnering with them in their data-centric AI journey. iMerit is headquartered in the US, has more than 5,500 employees, and works in domains like autonomous mobility, autonomous vehicles, medical imaging, conversational AI, and document AI. Very recently, a significant milestone was reached where iMerit has classified more than 500 million data points across various data modalities. iMerit was founded in 2012 by Silicon Valley entrepreneurs and has the Dell Foundation and Khosla Impact, amongst others, on our board. I would now like to give a quick overview on data annotation. Data annotation is a process of structuring and classifying data so that an ML model can distinguish between the human and the background, so that a model can see the difference between people and vehicles, so that a model can understand the actions and intents by analyzing the pose of a human. It can also help medical imaging in diagnosing and various conditions and diseases by providing highly accurate ground truth data. Data annotation also helps machines to parse and understand text by providing near NER and NEL capabilities within the raw data. I would now like to take you through the typical journey that a company undertakes as they go about building their training data. They start small with in-house teams, but very soon they realize that they need tool providers who can help them annotate complex data objects. Many of these tool providers provide tools that are very specific to a certain data modality. This process continues till the company reaches a point where they have a lot more data that needs to be classified that can be handled by the internal teams. This is when they reach out to workforce providers, and these workforce providers bring in trained annotators who can quickly be taught to execute a certain workflow. But as this journey continues, these companies soon reach another inflection point where they realize that the workforce providers are no longer just sufficient, and they have to work with solution providers like iMerit. To understand this better, let's first realize that nearly 60 to 70% of the time that is spent in developing an AI model is actually spent on data. It is spent on gathering this data, cleaning this data, structuring it, and managing this data as it flows between various ML processes. All through this entire process, it is very important to ensure that data is maintained at a very high quality to ensure that the model's performance is the best possible. Keeping these demands in mind, companies look at solution providers who can typically provide a one-stop solution for these various needs. Additionally, solution providers can allow a company to dynamically scale their AI requirements and bring in a lot of external expertise and experience given the various domains that these companies work in. Let us now understand the typical ML lifecycle and see the role of data through this life cycle. Training data is used to build a model. Multiple such models would be built. And finally, one of these models has to be chosen by evaluating it against a test data set. And based on the performance, a model is selected for production. This model is further tested by evaluating it against fresh production data to ensure there's minimal training serving skew. Once deployed, this model is continuously monitored and observed to ensure that the model's performance is above a certain threshold. The moment this performance dips, the model has to be retrained with fresh production data. What you saw in the previous slide is ML Ops, but please do remember ML Ops has two parts, ML Model Ops and ML Data Ops. In ML Model Ops, the focus is on training models and tuning them and deploying these models. Whereas in ML Data Ops, it's all about data and data that is used for training, data that is used for validation, test scenarios, and monitoring the performance of these models once they reach production. Now that we have an overview of annotation, let's understand what happens in data-centric AI. The traditional approach to building AI systems has been to train a model to reach a certain baseline performance and then tweak and tune that model to get incremental increases in performance. But unfortunately, most of these models fail once they're deployed. An alternate approach is to take a model, bring it to a certain baseline performance, and then train it against various data sets that truly represent the environment within which a model has to operate. This approach has shown great results in production and is now becoming the paradigm for AI production. Now that we understand data-centric AI, let's understand why we need a lot of data. If you look at this graph on your left, you will see error plotted on the y-axis against the training data set size on the x-axis. Both these parameters are in log scale. In the small data region, the model's performance is the worst with the highest amount of error. This is the region where models are being tested and lots of R&D is being conducted. As the training increases, the model's performance improves and the models reach a certain threshold where they are now selected to get into production. As they are trained to get into production, the error drastically reduces due to the exponential increase in the training dataset size. Soon these models are selected to get into production, and once within production, the models are continuously trained to improve the performance. But they will hit a zone of irreducible error. And this irreducible error is called an edge case. Now that we understand the need for lots of data, how do companies go about getting this data? Companies can choose to collect this data, but that's a time-consuming and expensive process. Companies can also choose to leverage publicly available data sets, which is a very good approach, but please do keep in mind that many of these data sets have errors in their ground truth, and these errors impact the performance of the ML models. This was a study that was conducted recently where multiple publicly available data sets were evaluated. Some very popular data sets like ImageNet were included in this evaluation. The study concluded that close to around 5% of the data within ImageNet is incorrectly labeled. ImageNet has 14 million images. That is a large number of error cases. To give you a sense of some of these errors, look at these images. Here, a frog is wrongly labeled as a cat. Imagine how a model would perform if it was trained on this data. Since using publicly available data sets comes with its own risks, another popular approach is to use augmentation. There are two major ways in which data can be augmented to increase the training dataset size. One of them is by using various manipulation techniques that are very specific to the data modality, that is images, audio, or video. In this example, in the computer vision space, image filters and various transformations can be used to transform an original image into various ancillary images, which are then used for training. A similar approach can be done with deep learning techniques where GANs are used to generate images based on original images. This is an example from Waymo where a point cloud is taken and it is augmented in multiple ways to improve the dataset size that is used for training. The point clouds can be aggregated, they can be scaled and randomly flipped, or various levels of noise can be introduced to increase the training dataset size. Another approach is to use deep learning to generate images, which is a very popular approach when you're trying to balance a data set and make sure that the data set is evenly distributed amongst all the classes. It also helps in minimizing the bias that is prevalent in many of these data sets. It is very important at this point to also understand the need for data set management. You have a lot of data that is collected, and this data has to be reused across various model training versions. And hence, data versioning becomes important so that you can reuse this data. It is also important to understand the data distribution and the bias inherent in the data. And there are various tools provided by multiple companies that help you in all of these processes. You can also use various curation tools to actively train your models to quickly perform a certain task. Now that we have a sense of data-centric AI, let's look at edge cases. Edge cases are those rare and unique scenarios that occur in the data that an AI system is processing. In many situations, these edge cases severely impact the performance of an ML model. To understand the impact better, look at this graph on your right. As you can see, the majority of the classes have a lot of instances, and hence the models are well trained for these head classes and well tested. But as you go towards the right, this tapers to very few training instances for these classes, and hence very limited training, and correspondingly, there are gaps in the testing. This traces back to the way data is collected. If you look at this distribution of a publicly available data set that is used for face detection, again, you see that there is a problem of a long tail in a data set's distribution. Here, the data set has a lot of data for the majority classes, but for those unique classes, there are very few samples. And typically, when a model encounters these unique classes in the real world, that's when the errors and the failures happen. Let's understand edge cases with the help of another example. This is taken from an AV use case where an autonomous vehicle is trained to recognize stop signs and take appropriate actions. The ML models are well trained and well tested, but as soon as they are deployed, the AI system is faced with stop signs that are either covered with snow or graffiti, or maybe blocked by trees and branches. In all of these cases, the ML model has to accurately determine that this is a stop sign and reliably take the appropriate action. In this real-world incident, a user of a self-driving vehicle reported that their vehicle would always stop when they cross this particular building. Turns out that the logos around this building look very similar to stop signs, and this was affecting the performance of the ML model. You could dismiss this as a one-off case, but there are 95 such locations in just 5 states across the US. Imagine the chaos that could ensue with these vehicles stopping whenever they cross these buildings. This is another example where an AV system has to look at this particular scene, understand that these objects can be safely ignored, and process the scene accordingly. All of this has to happen within a fraction of a second. It is very important to highlight the importance of experts in resolving edge cases. They provide various insights to the data that is already available, and these insights can help resolve many of these edge case scenarios. In this particular example, a customer wanted to train a model to distinguish whether the outside environment was cloudy or sunny. A lot of training data was provided and the models were trained appropriately, but the performance didn't meet the required benchmarks. That is when the team decided to use the shadows that were cast by cars and other objects within the image to act as a feature point for the ML training process. Once these features were included, immediately the model's performance improved drastically, and very soon this model was deployed. Depending on which part of the ML lifecycle you're working on, an edge case could have different connotations. In the collection phase, it is about incomplete or insufficient data that is being collected. In the labeling phase, it is about incomplete attributes that are being classified. In the training phase, it is about incomplete testing against various scenarios and classes. In the deployment phase, it's the actual performance of an ML model when working on real world data. I would like to highlight some of the challenges that companies face when handling edge cases. The biggest challenge is a lack of clear guidelines that help indicate the training process and the testing process. This is because there is an incomplete understanding of the operational design domain. And with these gaps in the guidelines, a lot of errors occur once the models are deployed. There is now a concentrated effort in reducing this problem with the help of standards like UL 4600 and the latest ISO standard around safety of the intended function. Another problem area is in having a very tight and traceable feedback loop between when an edge case is reported and to the point where that ML model is retrained on that particular edge case. Once an ML model is retrained, the scenario under which it failed has to be replicated. This is where synthetic data and simulations play a huge role. Last, it is very important to validate the system once a particular edge case is resolved. If you look at this breakdown of the ML models that are used within an autonomous vehicle system, you will see that there are multiple models that are used for object detections, lane markings, and trajectory generation. When an edge case is resolved in one of these models, it has ripple effects on the other models as well. And hence, there has to be a comprehensive system testing. There's a growing use of synthetic data to fill in the gaps that exist in training data that is used to build ML models. Industry reports state that by 2030, synthetic data would have completely overtaken real data as being the primary source of training material for ML models. This is an example of a synthetic data in action. A simulation of a scene is created, and once the simulation is created, very quickly, various perspectives of the same scene are quickly generated. Contrast this with the time taken to collect data under these various scenarios. Now that we understand edge cases better, it is also important to highlight the importance of edge case platforms. There is a growing need for a systemic and intelligent way of handling edge cases and extracting all possible intelligence out of the edge cases that are reported. Ideally, the edge case reports that come from various sensors, in the case of AV or any other data modality, are collected along with process guidelines and test plans. And all of this are fed into an analytical engine whose primary use case is to generate various scenarios. Ideally, a knowledge graph is the best implementation of an analytical engine as it allows various scenarios to be mined. Once scenarios are created, they are used to understand the synthetic data that has to be generated or the augmentation techniques that have to be incorporated to improve the training data coverage. These scenarios are also used in test case generation and anomaly testing, by which the performance of a model is improved considerably within the testing phase rather than seeing failures once deployed. This is a generic workflow that can be used for an edge case platform, where edge cases are collected at various stages, the data is extracted and sanitized, and then scenarios are mined out of this data. Once these scenarios are laid out, simulations are created of these scenarios, and then the models are trained to handle these scenarios by using augmented data. Once the models are trained and validated against these scenarios, they are deployed into the real world. To summarize, edge cases are the biggest showstoppers in the production phase of AI. The major bottleneck in resolving edge cases is in the availability of training data that truly replicates the real-world conditions. It is also important to have an edge case platform that can systematically improve the performance of an ML model when it comes to handling edge cases. With this, I come to an end of my presentation. Thank you.